Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Cesare Cinelli. Cesare is one of the founders of the SMT initiative. He has worked in the CVC3 team, the CVC4, model evolution calculus. He did many work in automated reasoning, and today he's going to talk about his model checker for called K-INDUCTION.
Thank you. Thanks a lot for the invitation, Leonardo. I'll tell you, I'll mention K-IND, but I'll tell you about the research that we've done around this model checker, which we hope is general enough that could be used also in other contexts. Of course, we have implemented it in the context of our K-IND model checker. This is a program lasting several years now that has involved students and other collaborators. I'd like to acknowledge these ones. Former student of mine, George Hagen, a current visitor from Onera, France, Pierre-Louis Caroche, and two postdocs, Yatinge and Teme Kazai. So just to put this in perspective, our goals here are, well, pretty much the usual ones in verification. Make verification practical, in particular improving performance and scalability, but we are focusing on embedded software. For the simple reason that, well, two reasons. One, it's generally easier to reason about embedded software, and two, it's more critical to prove such kind of software correct, or at least potential users are more interested in that. We also focus on the simpler problem of proving safety or dually invariance of properties, and we look at just synchronous systems. Our goals were to capitalize on initially when we started, and they still are, to capitalize on the various improvements and enhancements in automated reasoning to, in particular, they go beyond the sort of propositional logic-based approach that have been common in verification, in particular in model checking, going back from symbolic model checking using BDDs and then set-based approaches. And of course, the key technology for us is SMT, which allows us to reason about logics that are more powerful than propositional logic. One of the things that they give us, SMT techniques, that one of the pluses that they give us is that we can easily reason indifferently about finite state and infinite state systems when we use them. So, well, what is the general approach if we want to do SMT-based safety checking? I'll be calling it safety checking because, again, to stress that that's what we're doing. Given some formal description of a system, M, and the property that we want to show, by system I mean transition system here, convert that automatically into some fragment of first-order logic with built-in theories for efficiency reasons, and try to prove or disprove the property automatically using inductive arguments. Of course, we like to use SMT solver as the main engine. One of the bonuses is that using this technology or these technologies allows us to work well both with control and with data properties in systems, which is usually not the case, or didn't used to be the case for previous approaches. Let me give you very little technical background. This is mostly notation. This is stuff that at least the audience here understands and knows well. So we can look at transition systems as usual as defined by triple SIT, where S is the state space, I is the set of initial states, and T is a transition relation over the states that defines the behavior of the system. But as I mentioned, we would like to encode such a system in a suitable logic. So for generality here, we can consider, in fact, all of the approaches that I'm describing here apply to any logic where you have decidable entailment. Okay? Any logic, in fact, when you have efficient decidable entailment. So you can think of propositional logic if you want to, as in any of the SMT logics, or other logics such as the EPR fragment of first-order logic. Let's assume that we have a set of variables in this logic and some distinguished terms that we call values. Okay? Now, as you all know, typically in such a setting, then you can encode states as tuples of values. The set of initial states can be represented precisely, usually by a formula that is satisfied exactly by the tuples that represent the initial states. And then you can, or we assume that you can encode the transition relation by a formula in this logic into tuples of variables, n tuples if the states are represented by n tuples, one for the current state and one for the next state. So standard stuff. State properties, of course, can be encoded as formulas over an n tuple of variables. Okay? So the syntax here, the notation that I'm using, for instance, for the variables, it denotes just that. I of x is a formula whose free variables are among x, the vector x. Okay, so remember, we want to, if you're doing safety, we want to prove typically that a property is invariant for a system. So we're interested in showing, oh, I don't have a pointer here, okay. We're interested in showing that a given property is satisfied by all reachable states. Well, this is usually a hard problem, and so what we try to do is to approximate it by showing that a property satisfies some stronger conditions. For instance, a sweet spot usually is that if you show that a property is inductive, then of course you've shown that it is invariant. So you try to do that automatically. There are other notions here, such as validity and triviality in a sense, that also give you invariance. But these are, showing properties, the property have these things is usually simple. I'm mentioning them because they'll come up in the invariant generation procedure I'll be describing next. So again, this is just to introduce the terminology. The notion of inductive property can be extended a bit in terms of k-inductive property, where typically traditionally in induction, when you define a property to be inductive, you basically say, well, it's satisfied by the initial state, and it's preserved by one-step transitions. K-induction essentially says that the property is preserved by k-step transitions. So why is that interesting? Well, because inductive properties are zero-inductive in this sense, and well, there are properties, they are k-inductive for some k greater than 0, but they are not inductive. In fact, so a property is k-inductive and also is k plus 1 inductive. So there is a larger set of properties that we could hope to prove automatically to be invariant. And why can we do that in this setting? Because we are assuming that all of these guys here are formulas represented in our logic, and entailment is decidable in that logic. So to prove a property k-inductive, you just have to run this test and then to run this test in principle. In practice, of course, yes?
Is it true that if a property holds on a system, then it is k-inductive for some k?
No, this is what I was going to say next. And the answer is no.
Not even for finite state systems?
For finite state systems, the answer is still no. Although for finite state system, you can use improvements to the basic k-induction algorithm to show any property to be invariant based on the fact that the search space is finite. Okay? But for infinite state systems, there is definitely the case that there are invariant properties that are not k-inductive. In fact, k-induction is a fairly weak method by itself. It's very easy, it's nice. You can use SMT provers off the shelf, but it won't get you a lot. Okay? Well, which is why you want to improve on it. Now, of course, some improvements go in a completely different direction, such as interpolation-based model checking. Okay?
Which can also be used with k-inductiveness terms.
Well, of course. I mean,
you can come up with something k-inductive and
SMT-based model checking can prove k-inductive properties.
No, I mean you can use k-inductiveness with interpolants. That's what I'm saying.
And vice versa, in fact. It's one of the things that I want to discuss with you later. For us, it's a nice framework because, as I mentioned, it's simple to implement, and you can improve on it. These are the pros of using k-induction as a way to prove invariance. I mentioned these. Also, this is another interesting point. The base case of K-induction is essentially bounded model checking. So that means you're guaranteed using K-induction to find violations of the properties if they exist. Okay? What, of course, you're not guaranteed is to prove that an invariant property holds unless it is K-inductive. And this is as it should be, because in the infinite state case, at least, invariance is not a recursively enumerable property. I mean, the set of invariant properties is not recursively enumerable, so we cannot even hope to have completeness. What we can hope to have is to improve on whatever method you have so that the precision of the method is higher. That is, it answers yes for more invariant properties, for more and more invariant properties.
So you have a property that's K-inductive.
Yeah.
And there's a procedure that takes a K-inductive property and creates another property that's inductive. What's the size increase?
Say this again.
So for every K-inductive property,
Yes.
there's a stronger property that's inductive for finite state system.
Stronger property than is inductive, yes.
And
Possibly, yes.
So what is the, can you characterize the trade-off, or is there a non-trivial?
You mean practical trade-offs, or? Well, for me is that I wouldn't know how to compute that. I don't have a general mechanism on how to compute that property that you're referring to.
Take the K-inductive property and it gives you an inductive.
Probably do it if you had variable elimination.
I mean, you could do something like that if you do quantifier elimination, but
So the question is
it's not an
is that
efficient
the
method.
best there is, or is
No, there is
something
more.
else?
I mean, this is what I'm going to say now. So there are these cons that some properties are K-inductive, but very, very large Ks. So it takes a long time to get there. And if the transition relation is large, the unfoldings are going to eventually kill you. And as I said, some properties are not K-inductive at all. So how can...
Really true for what type of systems?
Say this again?
Flat state machines representing, I don't know, reactive systems, K-induction is good for. Programs with loops and recursive procedure.
No, we don't do program with loops at all because those are not transition systems in our sense, right? Well, you can convert them in transition
systems. So I'm asking, are those types of transition systems amenable to this? I mean, when you say some types of systems, do you have? I mean, what sort of systems does K-induction not work well?
We are, as I mentioned before, we're interested in embedded systems. In particular, we work on models of embedded systems. I mean, in our experience, we've been working on model checking, high-level specifications of systems that haven't been implemented yet.
So you're saying even for those systems, those embedded systems, their K-induction is good for some, but not for others?
Definitely.
Oh, okay.
Definitely. And it's good that you're asking me questions, but I'm going to tell you all these things as we go. I mean, this is part of the talk. Yeah.
You made the comment.
Sorry, this is just the way we work.
That's fine. That's
Sorry.
You made the comment that the set of invariant properties is not RE.
fine. For infinite state systems.
Why is that? I mean, I'm thinking that you can just start enumerating
because
them.
you have undecidability in general of...
But let's say, I mean, I can just start enumerating them, and then for each one, I can check whether it is inductive or not. So eventually, I would have enumerated.
No. I didn't say inductive. I said invariant.
Oh, I see.
Yes, of course, inductive property. The set of inductive properties is recursively enumerable, but they don't exhaust. Inductiveness is a sufficient condition to invariant. Right? If something is inductive, it's invariant, but not necessarily vice versa. This is why the verification problem is hard, because we want to prove inductiveness. We want to prove invariance, and then, well, we use poor man's version of invariance, which are, for instance, inductiveness. And when it works, it's great. When it doesn't work, we have to figure out why. So this slide is introducing an intuition here that allows us to do better. Okay? But again, better, not necessarily in a proven way. Okay? We don't have a systematic way to do this. So why is it that K-induction is not complete for invariance? Because you might have that the inductive step, which we can represent here as a satisfiability question, fails. Okay? So if the inductive step fails, means that a formula like that one is satisfied.
The last one is supposed to be not P of this xk plus 1.
Say this again? This is?
It has an extra argument xk, which I think is...
Oh yeah, I apologize.
Okay.
This is a spurious argument here. Thanks. Thanks for debugging. So if this formula fails, it's because we have a sequence of states along the transition relations where P is true for the first state, k states, and then it's false in the other one. If P is invariant, it must be that this sequence is unreachable. Okay? There's no other explanation. So one way to improve induction is to say, well, I don't want to consider this sequence. Okay? Eliminate it. Well, this is the general way you would like to do it. One way to achieve that is to strengthen the description of the transition relation. If you have a tighter description in your logic of a transition relation, hopefully that set as 0 there will not be satisfying any pairs, tx, x prime, and so you won't have that counterexample. So how can you do that? Well, suppose you know another invariant about the system. You can strengthen the description of the transition relation by just saying that, well, I want the predicate of x also that it satisfies the invariant. I don't want an arbitrary x that satisfies this formula. It also has to satisfy this invariant that I have. Now, the tighter this invariant, the better this formula will be at discarding irrelevant, that is, unreachable states. Okay? So this is one possible way to improve k-induction. In fact, it gives you a lot of power if you're able to generate good invariants. The question is, of course, how do you do that? Okay?
So you describe it as strengthening the transition relation.
Yes.
But a different point of view of the same is to bootstrap invariants from simpler invariants.
What do you mean by bootstrap?
So J is an invariant, and when you check k-induction, you basically just add the J sub xi in these formulas.
Well, yeah, I mean, this is the effect is the same. You're adding J here everywhere, okay?
So is there a way to bootstrap k-induction? So here J is...
Yes. I don't know the answer in general. I mean, what are good ways? I can give you one way that that we have been using, and I'll get to that later. Well, maybe I'll get to that later, depending on your question. So let's leave some suspense here. Okay, so again, there are stronger approaches to prove invariance using inductive arguments. Well, again, interpolation-based model checking, abstract interpretation, PDR now, and so on. The good thing about k-induction is that it's simple, but you can improve on it and make it as good as other approaches by adding invariants. How do you generate invariants? There are a lot of ways. One thing that we try to do, it's on the face of it's fairly silly, but it worked rather well for us. The key is, of course, in how you implement it. So what is the idea? Suppose you don't really know better. What you could do is to say, well, I'm going to generate just a large set of formulas that could be invariant just by luck. And I'm going to check them for invariance by checking that they are k-inductive. But I'm going to do this as efficiently as I can and hope to get lucky. And then any invariant that I can get out of this, I'm going to be using for k-induction. Okay? Now, we call this a smart brute force because it is a brute force mechanism. But to make it effective, you have to be a bit smart about it. So, sorry?
Do you use something like Houdini?
So, something like Houdini, okay? Or something like, what is that system, DICON, right? Where you have some heuristic ways to generate loss of candidate invariants. But then the difference here is that we actually prove these to be invariants. For instance, in DICON, it's just given to the user, now user has to figure out.
DICON is just a way of throwing out a bunch quickly. by doing execution? On
Well, we throw away a bunch very quickly, and then the remaining ones we also prove to be k-inductive to be sure that they are invariant. The key here is very quickly. And starting with a very large set. So you want to implement your large set of conjectures, C, as compactly as possible, and sift through it as quickly as possible. And as SAT or SMT solvers are really good at this kind of stuff. So we capitalize again on our technology. So what is our scheme? We have a general invariant discovering scheme that again assumes an encoding of our system in a given logic. And then the scheme is parameterized by a template formula, R, which represents some binary relation over a domain, one of the domains of your system, okay, over your types of your system. We assume this method, the scheme, is parameterized by the procedure you use to generate the candidate set at the beginning. Use whatever you want, okay, whatever method you can come up with that generates terms that might be interesting to instantiate the template with. So let me give you concrete examples. So one example of R would be, sorry, I got it backwards here. One example of R would be implication. Okay, so implication over Boolean terms. Another one could be standard less than over arithmetic terms. Okay, so if this is the template, that is implication or less than, the arguments that we could put in there are, well, whatever arguments of the proper type that your logic accepts. So in an SMT logic with arithmetic terms, then you could have examples like this. Notice that the instantiation can give you arbitrarily sophisticated formulas depending on the terms you start with. So here I do have a less than that I'm instantiated, but in fact I have some control embedded in it because I can use ITEs. And similarly here, implication is not just between Boolean terms, but between arithmetic terms. Okay?
This is highly explosive, right?
Yeah.
Trying to truly generate.
No, I'm just saying we allow this. Now, if you want to use our system or approach, it is your business to come up with the initial set. Then we can take it from there. Okay? Now, right now in our experiments, what we do is we look at the description of the system and we consider all possible subterms. Obviously, this is not going to scale. And in fact, there are other things that you want to throw in that are not just subterms, okay, that you can come up with. But let's assume you have a way to generate that set. Then how does the mechanism work? Well, we use, in a sense, BMC, or the base case of K-induction, to discard as many of these conjectures as possible from a set by finding real counterexamples, okay, to the invariants. Once we have filtered that set down to one that we are happy with, or that heuristically is small enough, then we try to prove the remaining elements of the set to be K-inductive for some K. The ones that we fail with, just conservatively throw away. The ones that we succeed, we keep. In the process of doing this, if the initial generations of terms is not too smart, will give you a lot of trivial invariants. Trivial in the sense that I mentioned, well, that I flashed you before. Those are not really useful. They are invariants, but they're not really helpful. So a third optional phase could be try to identify those and discard them, because they're just junk. Of course, identifying trivial invariants is expensive, so sometimes you can just leave them there. Okay, it's really, it depends on the particular.
Not unlike a learned flawless, right? I mean, maybe it would be good to put it in anyway.
Very good. So in fact, this is why we don't discard them often, because some of the trivial invariants are not eliminating any unreachable states. However, they're lemmas, and so they are helping the set. They might actually end up helping the SMT solver. Very good. Only the valid ones are the ones that probably don't help all that much. Okay, so the mechanism is just what I described here. Well, we have some animations, but it's not going to give you much more than what I told you. Suppose these are all our conjectures. if we take their conjunction, we're making a very strong claim here. We're saying all these guys hold. We test them in the initial states, okay? And sure enough, we're going to get lots of counterexamples that allow us to remove some of these candidates. And we do this until we reach a fixed point for initial states, that it is all the conjectures that we have do hold for all the initial states. When we repeat the same process, sorry, I'm going quickly here because I've already mentioned this stuff. We repeat the same process for states reachable in one step, reachable in two steps, and so on. Where do we stop? Well, heuristically, we stop if when we are at frame k and we go from frame k to k plus 1, nothing changes. That doesn't really mean that we found a good spot. It's just heuristically one that we decided to do. Why is that? It's possible, indeed, that from k to k plus 1, nothing changes, but maybe some of the stuff could be, as counterexample, some bigger k. Okay? It's better, better heuristics could be used to do that. That works for us for now. So once we get to this point, then the conjectures are conjectures that possibly are invariant. We try to prove them k-inductive, simply by doing the k-induction step. Anything that falsifies the k-induction step is thrown away, again, to be on the safe side. Anything that remains has been proven to be invariant. One thing that I want to stress that I didn't say is that, notice that we work with conjunctions. We don't do them one at a time. We do them all together. Why? Because when you get a counterexample, you usually get lucky. A counterexample eliminates several conjectures at the same time. So you want to throw away as much stuff, as much chunk as possible. Also, as you know, proving something stronger by induction is usually easier. So if you try to prove that all of them are inductive, all the ones that have remained, it's usually easier than to prove it individually. Okay, so some of these conjectures have been generated. We're done. Okay? As I mentioned, the question is, how do we do this efficiently? By representing the set compactly and by processing it, that is, the set of correct conjectures, efficiently. So we have two algorithms for doing this, which depend on the size of the domain in question. So remember, the template is a partial order with respect to some domain. So with the Booleans was one example, the integers was another example. We have a general mechanism that works for any binary domain and for any non-binary domain. Really, the distinction is here finite up to a certain amount and greater than that. But binary is the sweet spot, really. Okay? So I'll tell you about, I'll show you about the procedure that we do in the binary case. And then, again, you can imagine, well, examples will all be about Booleans, but it could be any binary domains. To talk about that, however, I need to introduce a notion before. So consider that we have a set of terms over the domain that we're working on. We can, and we have a sequence of valuations of these terms. So in our algorithm, the valuations come from the counterexamples. But now just consider any valuation. So for instance, if we're talking about arithmetic, consider these valuations for the terms. Okay? A sequence of size 3. Each of these sequences induces a partial ordering over the terms, which is just the pointwise extension of the partial ordering over the domain. Okay? So here I have that the term x is less than x plus 1, but y is less than 3y, and so on. Okay? So having this ordering is going to be helpful in what I'm going to discuss later, right now. If we look at the Boolean domain as an example of a binary domain, our set of conjectures is going to be a set of implications between terms. So C here is the set of terms we start with. Conjectures will be implications between these terms. So we start with the strongest conjecture possible, that we say all terms are related. They all imply each other. Why? Because some conjecture can be expressed linearly by just a chain of equivalences. Okay? So we start with this chain. We're going to represent our conjectures as graphs, as DAGs in fact, where each node represents an equivalence class of terms with respect to the ordering that I have discussed so far. Okay, so a partial ordering induces an equivalence class. So every terms in the nodes are related to each other. Okay, and then links between the nodes are going to represent the fact that every term in one node is smaller than every term in the other node. Okay, in the partial ordering that we're building with these assignments. The partial ordering in question, which is built out of the sequence, will be built incrementally as we build the sequence. So we start initially with the empty sequence, which means everything is in there, everything is related to each other. Then we extend the sequence with the first counter model that we get in the process I described before, then with the second, and so on. So we'll have a graph that starts to be really compact and starts growing as we get counterexamples to the less than relation. Say it again?
You're familiar with Van Eyck's method?
Yes.
Okay.
In fact, I should have said this at the beginning. This work is inspired by that paper. For those, since you know that, what we do is everything that method does and more. We definitely identify all equivalences between terms, which was the original motivation there because they were doing circuits. But we do more than that because we also do implications instead of equivalences. Okay, so suppose we have this situation here. So the conjecture is all terms are equivalent, and assume that we get a counter model, or a model that gives these values, 0 for false and 1 for true, to the terms. So what does that mean? That, well, it's not true that these terms are equivalent, okay, according to the ordering that we're building. So we break that bubble into the ones that we have seen to be false so far and the ones we have seen to be true. So what do we know? With the current evidence, these guys could all be equivalent, and these guys could all be equivalents, but definitely these guys here are not equivalent to guys here because we have a counterexample. But as far as we know, everything in here could imply everything in here. We don't have evidence to the contrary yet.
Everything in here, do you mean a conjunction of all those guys?
Well, each one. This is an equivalence class.
Individually.
Each of them individually can imply that. Each guy in here could imply that. Remember, we are assuming that these guys are equivalent, so pick a representative, whatever.
Right, so that edge
means any term in here.
Representing a quadratic, m times n number of
Exactly. So this is the compactness that we get.
Okay.
We are representing now a quadratic number of implications linearly. Okay. Next counterexample. Well, some of the assignments here are going to break some of these bubbles again. In particular here, both bubbles are broken. But what do we know about these two bubbles? The same thing that I mentioned before. Well, they're not the terms in here are not equivalent, but I only have a counter argument for one direction. For the other one, I have to place conservatively and maintain it so far. What about these guys? Well, these guys can be connected by remembering the previous link. So the previous link is somehow, in a sense, inherited by the new guys. And the point of our algorithm is coming up with a systematic and sound way to do this inheritance. I mean, that's the non-triviality, the non-trivial part there. And so, but if you look at in terms of ordering, notice that the links respect the ordering. Okay, these guys are smaller than these guys in the pointwise ordering between these pairs, and it's true for all that we get here. Okay. The trick is that we don't want this link. Technically, this link is possible, right? Because everything here is smaller than everything here, but this link is redundant because we have these two. So the algorithm also tries to minimize redundant links. Now, look at this as a conjecture. What is it saying? It's saying I have quadratically many implications between these two guys, between these guys, and none between these guys I need to represent because they are a consequence of transitivity of my partial order. So we do this in a sense modulo transitivity, and we maintain this set of conjectures very compactly. When we give it to the SAS solver or the SMT solver, we literally do this. Here, this is a chain of inequalities. A chain of equivalences. We pick one guy and we say that implies some representative here, and so on. So we get a very small set of formulas that represent our large conjecture. Okay? And, well, again, we continue to, there are other cases like this one where things are broken this way, and, well, or things are broken this way, but there's actually a finite number of configurations that you need to consider. Why? Because since you're in a binary domain, there's only a finite number, well, since you're in a finite domain, there's only a finite number of ways to break the graph and inherit the links. In an infinite domain, that's not the case, so this algorithm would not work. In particular, when I have to connect two new nodes, I have to figure out which of the ancestors I should connect these nodes to. In the binary case, I know I need to look at most at the grandfather. In the infinite case, I could have to go, an unbounded number. I would have to look at an unbounded number of ancestors. So this algorithm doesn't work in the infinite case. The way we're doing it is linear in the number of nodes at edges, and this is most likely, we haven't done a precise analysis, at the cost of optimality. That is, sometimes we do get those redundant edges that I mentioned. It's just too expensive to make sure that you never have redundant edges. If you throw a few redundant edges in the final formula, it's really not a big deal. Okay, so.
I'm sorry, this might be too. But how does this relate to Stallmark's method, if at all? Isn't there you're conjecturing, or you make a choice that like two formulas are equal? You sort of look at the implications. I'm trying to understand what this graphically represents.
The obvious answer is Stallman's method is a way to check satisfiability. Here we're trying to show equivalence between these guys or implications. So I don't see an immediate connection. Maybe there is one, but I don't see it right now. All right, in the numeric domains, we have generalized this to numeric domains. We can use the graph. However, we can use partial order sorting. That is, well, again, we have all these tuples. And these tuples, which represent countermodels I've seen so far, are associated to classes of terms. And these are the terms that we want to order. Okay? So we order terms according to these tuples that they are associated with. And the ordering is refined. So the important thing here is that this is an incremental step. Every time that you have a new countermodel, then you have an ordering on a slightly larger tuple, well, larger by 1. However, the current partial ordering that you have is changed with respect to the previous one only in a number of small ways. Okay? So this allows us to, this incrementality allows us to do some operations quickly. And in fact, we've come up with a new partial sorting algorithm that, well, it's cubic. But it's cubic in the number of nodes, the height of the partial ordering, and the width.
In the numeric domain, the partial order is just the arithmetic.
The pointwise extension of less than. The partial ordering is over tuples, remember?
Oh, yeah, that's right.
So the ordering over the individual elements is just less than. And over tuples is the pointwise extension. Okay? So, this tuple is smaller than this one.
But another way of saying that, is that you have some language and you're trying to find the strongest theory expressible in that language that's consistent with your evidence, which is your tuple.
The theory being the conjecture, yes.
Compact representation of that theory.
Definitely, yeah.
So.
Yep. The idea in general is not, it's fairly simple. As I said, the contribution is in the actual mechanisms that we have implemented.
Trying to deal with a large theory. Right, something that's going to be at least, quadratic in size or whatever in the number of terms that you have to deal with.
That's right.
So, so the methods used for Salra,
For what?
Sumit and Salra have the invariant generation from templates that use counterexamples to define sets of terms. So your method have these directions.
See, that's why it's good to give talks to these audiences. I'm not aware of that paper. Yesterday I discovered another paper I wasn't aware of.
So the main idea there is that you want to learn a function. So you have input-output pairs.
Oh, so you're talking about the learning algorithm. Okay.
Yeah, right. So and so you learn these. What are the possible invariants you can?
So at any time they have a conjecture that is based on what they've seen so far, and they modify the conjecture. Is that what they do?
Basically.
I mean, you could see this as a learning algorithm in that sense, right? As Ken says, you have a theory and you're trying. The theory explains your observations and you're trying.
Which is your SMT solver.
Sorry? Use the SMT solver as your tutor, right? The tutor is giving you the answers of. Is giving you well, in this case, it's only done by counterexamples, not by positive examples. So it's a very limited form of learning by counterexamples. But it's essentially what we're doing. Yes?
Maybe I didn't understand that part. So when you say counterexamples, these are runs by the reachable states.
So imagine the first conjecture. The first conjecture says all these terms are equivalent. Okay? So you try to prove that in the initial states. So when you start, you say the initial state condition implies that. Sure enough, you're going to get a lot of counterexamples. Throw away that. And you keep doing it. Sorry?
Yeah,
yes, but a very restricted kind of learning.
Okay, but counterexamples to input-output.
It's reminiscence of version spaces, some ancient learning techniques, except that in version spaces you start with an under-approximation and an over-approximation and use your positive and negative counterexamples to have them converge. The problem with version spaces is that often, actually, they will go like that. In this case, we're just doing one direction. We start, from bottom up. We start with a very, very strong conjecture, and we weaken it until it explains all the observations that we see. And so, as I said, in the numeric case, you can do similar things. We have an algorithm that on the face of it is cubic, except that in practice, h, the height of our graphs, is usually small. Because it depends on the kind of problem. It doesn't the good thing is this measure does not depend on the size of the initial set. Well, it doesn't depend quadratically on the size of the initial set.
N is the initial set.
Sorry? N is the number of nodes, and so the initial number of terms. It depends on the intrinsic properties of this ordering. So you can get lucky and have very flat situations, or you go very quickly.
Right. But the height width will be greater than equal to n.
Say it again?
H times W is greater than equal to n.
Well, they are related, right? Suppose the height is always 1, then the width is exactly n, right? Or vice versa. Suppose the width is 1, then the height is going to be exactly n. So in the worst case, we get quadratic, essentially, for us. Okay, in the best case, we are quadratic.
No, Nikolai is making an important point. He's saying that HW is at least order n. So really there's
by itself.
Right,
is order
so
n.
it is order n squared.
So this is, yes. So okay. I said before that we want compact in the sense of less than n squared. We don't quite get that.
Okay.
But this is actually quite good because existing learning algorithms are effectively cubic. Existing partial ordering algorithms are effectively cubic. But for our purposes, often h is bounded. And so, in fact, this is quadratic. It's good enough. Experimental results. So we work with, our kind model checker, we created a module that generates invariance and integrated it into the model checker. In fact, one thing that I haven't described to you is that the real implementation now is incremental. Incremental meaning that we don't wait until the end to produce the invariance. For every k, we're able to produce invariance. Okay? which means that since kind is parallel, we feed invariants as they're discovered to the kind process as kind is trying to prove by induction the property you started with. So which means that as soon as invariant generator is given to kind uses this to strengthen k-induction. And often this leads to effectively making the property that you wanted easily provable with the invariant. But again, you don't have to wait until the process finishes.
Yes, but so you're using this, Houdini-like technique. You're generating counterexamples to induction, which go into your building your graphs and so on. Do those counterexamples to induction come from k-induction or one induction?
K-induction.
K-induction, right? So that means that you could have had there are conjectures you could have thrown out at k equals 2 that will come back in at k equals 3, right? It's not
the ones that we've thrown out in the BMC run, that is the base case of k-induction, are definitely in.
Right.
Those that's exactly what we do. The ones that we throw out at k, before I said, the ones that we falsify in the inductive step, we throw away. We don't actually throw them away. We keep them around, hoping that they are k+1 inductive. That's exactly the process. The ones that we prove for k, so what we do, at k equals 2, some stuff is not k-inductive, set aside. The stuff that remains, try again. Right? Set aside. Try again. At some point, some stuff is too inductive. And so we will succeed. We will always succeed because in the worst case, we get true. True is too inductive. And so, we will pass those and then move to the other ones. So there is always some stuff that we can do.
So you have some kind of a loop where you keep increasing the k?
Yes.
I see.
Well, there is a loop in the invariant generation, and there is 2 loops in the k-induction proper, that is in the model checker. The model checker is doing the base case and the k-inductive step also in parallel. Everything goes on in parallel. And then they synchronize at proper times to show you. So the k-induction step of the model checker fails, asks the invariant generation, do you have anything for me? If it does, then it uses them. When it succeeds, it asks the base case, have you found any counterexample? Okay, have you arrived to k? Because if you haven't, I have to wait.
Do you have some kind of a picture of this?
Yeah, I do.
I would love to walk through that.
Actually,
picture.
do you mind if we go over that picture later? Because I want to tell you about the results because,
Okay, yeah.
So we've integrated this in kind, and we work with Boolean invariant. I flashed you this. Kind works over, where is it? The input language of kind is the Lustre language. For those who know it, I don't have to say anything. Those who don't know it, it's just yet another language to express transition systems. Something like SMB. If you're familiar with SMB, I think actually we were inspired by Lustre.
No, I didn't.
No, okay, but there are definitely similarities. Okay, so except that you don't have a restriction to finite types. You can have infinite types. By infinite types, I mean, of course, mathematical integers is an approximation of machine integers and that kind of stuff. All right, so we produce invariants of this form where these guys are Boolean Lustre terms, or this forms where these guys are arithmetic Lustre terms. Excuse me. And again, notice that since we look at conjunctions on these invariants, double implication is effectively equivalence, so we discover equivalence between streams or even arithmetic equalities. In the benchmarks we tried, we had, about 1,000 loose benchmarks where we have a model and a single property to be shown invariant. If you run kind in a decent configuration here, in inductive mode that is trying to prove invariance, kind can prove 33% of these benchmarks, can prove these benchmarks to be valid, meaning that the property is invariant, can disprove 47% by finding an actual counterexample, and is unknown, cannot solve 21%. Now we throw in the invariant generators. And so again, no invariant, we can solve. If we now focus just on the valid or unsolved properties, under the assumption that the unsolved properties are probably valid. Okay, because we have run kind for a long time in B and C mode, couldn't find any counterexamples, they're most likely valid.
By the way,
Okay?
are Lustre programs finite state? Are they only
No,
Boolean
no,
numbers?
they're not
They can
finite
have
state.
integers and such?
Yes, yes.
But the theories that you're using are only integers and propositional logic.
Integers, propositional logic, reals. Well, in fact, you also use uninterpreted function symbols for convenience. They're not really needed.
Or what do you use on interpret function?
We represent, Lustre is a data flow language. So in fact, its variables are streams. And we represent streams as functions over the natural numbers in our encoding. It doesn't have to be like that. It's just convenient for us to do it that way. Okay. You don't. It's not necessary to achieve the same sort of results. All right. So that's the current situation. That is no invariance. If you throw in Boolean invariance, then we go from 61% accuracy to 77. With integer invariance, we go to just integer invariance. We go to 82. If we put them together, we go to 86. This might not look too impressive with respect to these two. You only go from 82 to 86. But let me point out that integer invariants often contain Boolean invariance in them, and vice versa. For instance, a Boolean invariance that might get generated, a Boolean conjecture that might be generated is one of the form x less than y equals true. So this is effectively a less than invariant that, however, you're recasting as a Boolean one, and vice versa. Okay, so these guys are not really disjoint. There's lots of overlap.
So your candidate terms now in these experiments, are these just terms that occur in the programs?
Yes, plus a few more terms that we throw in for good measure.
So do you have any idea what's going on with the remaining 72? What are you going to do now?
Yeah.
Supposing I gave you $1 million,
Yeah.
you say, okay, I want an answer to all 72 of them.
We want to produce smarter, improve the initial phase, the phase where we generate candidate conjectures. Okay?
So, but
We've actually done it in a follow-up paper that I don't have time to tell you about. For a lot of these systems, there's a business of modes. These systems have modes, which are essentially finite state situations. And when you encode them in Lustre, you lose mode information. And you can try to recover mode information experimentally and then throw in invariants that have to do with the modes that are not evident in the Lustre encoding. I can tell you about this offline. So we've done that, and we have experiments that show if you throw in these other guys that talk about mode invariants will be something like, if x is 1, then y is either 1 or true, or 4. Something like that, where x is encoding some mode and y is encoding some other mode. If you throw those in, well, you should not have lost those in the first place, but if the encoding is not so good, which is the case often, you lose them. If you throw those in, you get more mileage.
how much?
I can't talk about these ones because these ones actually don't have a lot of modes. We've done it for another set of benchmarks, and to those we go to something like 91%, 92. But again, no, these numbers don't mean much. I mean, I want to stress, these results might say something about the goodness of our method, or they might say something about the properties of our invariance set, right? I mean, there's always the usual issue of how representative these things are. However, one thing I want to say are we have an industrial user that is using Kind, our friends at Rockwell Collins, and they tell us they are quite happy with this feature for the sort of things that they do. So we just have anecdotal evidence that it is helpful.
Comment about this. I think you're downplaying how cool this is. This is very cool for the following reason. Now you have set a bar for any future sophisticated invariant generation.
Right, you have to be at least as good as the stupid
ones, right? Because this is so simple, all this stuff.
Yeah.
Yeah.
Well, again, in the spirit of not underselling our thing, the idea is simple. The execution is not.
Simple is the best compliment I can pay you.
Okay.
Yeah.
But the execution is fairly sophisticated to get that efficiency.
What's the timeout value to declare a benchmark and solve? What are we talking about?
Yeah, I forget now, but it's...
It was on the previous slide.
Oh, I did have it?
Oh,
5
sorry, I
minutes?
missed it.
120 seconds, sorry.
120 seconds.
Actually, I do have more, but again, you know.
Nothing.
Sorry?
What if you put it like to...
Yeah, well, it's nothing, but have you seen the benchmarks? Sorry, it's nothing means small?
Yeah. Yeah.
Yes, but have you seen the benchmarks?
No.
You know, maybe the benchmarks are not that impressive, right? I mean, they go from fairly small to moderately large, not huge.
If you double it, now you get 100%?
No, doubling doesn't help. I mean, if a property is not k-inductive,
Yes.
with respect to the transition relation and the invariance you have, doubling the time is not going to do it. Tripling, you know, go to infinite time. It's not going to prove it.
Okay, I don't know.
So the only thing that you can hope here is that you throw in more and more invariance.
You get a rapidly diminishing return.
Yes.
K-induction, right?
That's
You know,
right.
K equals 1, K equals 2, K equals 3, pretty good. You know,
Yeah.
you get a few out there, K equals 10,
Okay.
20.
But let me
That's
show
what I
you.
wanted to hear.
I have these
That's what
interesting
I'm
results
kind of
here.
wondering.
Let me, I want Ken to see these. For the valid ones, that is the ones that are provable without invariance, okay? Adding invariance accelerates stuff. As you're saying, without invariance, the percentage of properties, there are more than one k-induction, more than that inductive, that is k-inductive for real, is 14% in our set. When you throw in the invariance, we go down to 3. So you're really trivializing the property with these invariants, which just gives us a good measure that these are good invariants, okay? Because now here we can compare. In fact, it's also true for the other ones. Well, in what sense? For the unsolvable ones, we go from, I would conjecture k equals infinity, because again, it's not that, probably it's not that k is too big, we don't get it. It's just k does not exist. So we accelerate from infinity, again, to very small k. In some cases, we have 20, but I mean, those are rare, which again means that the invariants are high quality. And also gives you some hope that the smarter techniques you come up with to produce high quality invariants, the better this is going to work, right? Our architecture now accepts any invariant generator. So you don't like this stuff, give me your you plug in your invariant generator. As long as it is a stream generator, then everything is going to work just nicely. In fact, and I'm going over time, but I want to conclude with this interesting observation. So our users don't care about a single property. Right? They have 20, 30, 50 properties that they want to prove about a system. And they want to prove them all at the same time. I mean, they want to prove them all of them. Okay? So you can't prove them separately, just it takes forever, it's inadequate. You can try to prove them together by just as a conjunction, but then if any one of them is not invariant, then you're done. You know, the conjunction is false, and so that breaks away if you do it in this naive way. Okay? Also, even if they're all invariants, since we're doing k-induction, some can be k-inductive, even if they are all inductive or k-inductive, some might be inductive for a small k, some for a big K. So we have modified our induction algorithm so that it does something similar to what I mentioned earlier. That is, it considers the conjunction, but then it looks at the properties individually and throws those away that are definitely not invariant. It keeps the other ones and so on. Now, what happens if you prove a property to be one inductive? We throw it back in as an invariant while we're trying to prove the other ones. So the properties actually help each other. But a lot more than in the standard sense of, oh, okay, I prove them try to prove all of them at the same time, I have a stronger conjecture. There's a slight difference here, that once you prove one invariant, then you don't have the obligation to reprove it. You just throw in as an invariant, it cuts the search space like crazy. Often we're able to prove, using this thing, we're able to prove all the properties without generating auxiliary invariants at all. They just help each other. Which kind of makes sense because if you think how people write properties, often properties are related and some are in fact lemmas for other properties. Okay?
Who are your users?
Rockwell Collins.
Okay. They implement the designs in Lustre, or do you have? Like
they actually write their designs in Simulinks, and then they have produced a converter from Simulink models to Lustre models, and then they feed them to K-IND. So yes, initially they have a nice picture that they go to Lustre and then they went to SAL, NewSMV, PVS, Sol Prover, the commercial system, and something else that now I forget. Now they've added kind, and well, for what they tell me, they're happy enough for now with kind of just using kind.
I'm wondering if they gave you numbers of like how kind compares with the other.
No. They couldn't, even if they wanted, they couldn't give me numbers because this is all anecdotal, okay? That is, they've been playing with their models and so on. It's not like they've not done a serious study and comparison study, okay? They come and say, oh, we couldn't prove this with prover, but kind is just fine, or, oh, well, actually, prover is faster here, but we don't really mind because kind is fast enough, Again, I don't want to make any claim here that is the only thing that they need. In fact, they're keeping all the others, but in the latest rounds with all these invariants and so on, they said that they're quite happy.
So your tool takes Lustre inputs, but the method itself, can you say something about whether there's anything specific to Lustre?
No, not at all. In fact, my last slides talks about kind 2 that we have started developing that will be disconnected from Lustre. Just have a Lustre front end, and then we'll be able to accept other languages.
Maybe you can solve recursive predicates.
Maybe. We'll see. In fact, when we started, I thought that we could capitalize on Lustre-specific encoding to do better, and it turns out really it's not really necessary to be tied to Lustre.
Is the semantics of Lustre well defined, that there is agreement among pretty much everybody?
Yes.
What it means? Okay.
So Lustre is defined formally. One catch I should explain is that Lustre is a specification language, but it's an executable specification language. So it has real data types, meaning it has machine integers and floating points. And we don't really work with Lustre. We work with idealized Lustre. And so, we can't catch all. We have the standard unsoundness issues by...
So floats you model as real?
Real, so we don't catch underflows, yeah, that kind of stuff. However, notice, there's nothing specific in our approach. Nothing hard-coded in our approach that limits us this way. That is, once we get an SMT solver that's good enough with floats or with bit vectors, then we can just switch to the accurate semantics. Everything else works. I mean, at least in principle. In practice, we'll have to see, but okay. Well, you wanted the architecture. This is the main architecture, assuming just one invariant generator, but in fact, you could have several. And they all work independently. And also, the architecture is such that they synchronize only rarely, only as needed. This is very low latency. This guy is a BMC. It just shoots until it finds a counterexample. When it finds a counterexample, it tells this guy, I found a counterexample for property P1. So this guy knows that it can throw it away. When this guy proves a property, it double checks with this guy and says, I proved a property to be 3 inductive. Have you gotten to 3 yet? If you haven't gotten to 3, I'll wait. But if you ever write to 3, it means that there's no problem. I can really certify it to be K-inductive. Since this guy is a lot faster, this is just BMC. In fact, anytime the inductive step succeeds, it doesn't have to wait anything at all, because this guy, if K is 10 here, this is 200. The invariants are just sent in a message queue to, a general message queue to this guy. And anytime the inductive step fails, it looks for invariants. If any invariance has arrived, it's used. If no invariants have arrived, then K is increased. So that means that if the invariant generator keeps generating invariants, It's possible for k never increase more than 1.
When you say that the invariant generator keeps generating invariants, is it generating invariants or is it generating candidates?
Invariants.
So that, huh?
Yeah, those are, so basically, I mean, K-induction is also going on inside the...
Yeah, but this is just an artifact of our method.
But it is sending, it is promising when something comes across N3 there, it is promising this is truly invariant.
It's really an invariant. Right now we have we have worked on another invariant generation based on abstract interpretation techniques, which is still incremental in this sense. That is, it computes a postfix point, but instead of waiting until the final computation, that is, the postfix point is being computed, at any intermediate step, it tries to figure out if the pieces of the current abstract elements are invariant. If they are, they're sent back. They're sent to the guy. So, I mean, any incremental invariant generator will plug in here. Again, but they have to be invariant. That's the meta invariant that the system uses. Well, the summary, I don't think I need to give to you. Future work, kind 2 I mentioned. We want to work on more invariant generation techniques. One of the reasons I'm here is to pick people's brain. I'm going to try to do that with Ken. I think we could use interpolation ideas to generate more invariants.
Can we go back to the previous slide?
Yeah.
No, the architecture slide.
Oh, sure.
So, if all the candidate business is happening in the right box, then why is there so much time difference between the base step process and the inductive step process? I mean, they're all they're doing is unfolding the program case steps, right?
That's a good question, but let's ignore this for now. Suppose we didn't have invariants.
Okay.
The base process is just doing BMC.
Okay.
This is doing real work in a sense, because it's trying to prove that a property is k-inductive. And unless the property is k-inductive, or say zero-inductive, it's going to fail, and then it's going to increment. Okay? So it's always going to generate larger and larger traces.
But that's the same thing?
Yes, but this starts from the initial state.
That's true.
The initial state, especially if your initial state is small, it's going to generate very few traces. Right? Here, in induction, you don't make any assumption on the first set of states. So it can be anything. There are a lot more solutions here than there are here. So that means a lot more to do to prove stuff or disprove it than there is here. I mean, it's the reason why BMC is really efficient as opposed to model checking proper. I mean, when you're trying to prove something that something holds, it's a lot harder than trying to find a counterexample. Now, of course, if the system is, if the model is big enough, even BMC might slow down or die because you're doing unrollings. But then the usual techniques can be used, like abstraction, actually as abstract, one form of abstraction where you actually don't work on the real transition relation, you work on an abstract one. If you find a counterexample, you verify that it's a real one. If it's not, you refine the usual Seeger stuff.
What is the abstraction that you do there?
We just do, what is that called? I forget the name, but it's Lustre programs are defined in terms of equations. So every stream is as a definition. So we throw away definitions. If you look at circuits, it's like considering a signal to be an input signal. You throw away the subcircuits that define it. Okay. And then when we need to refine, we throw in stuff. Well, of course, you do it in a way that capitalizes again on the SMT solvers. For instance, as usual, if we find a counterexample, then we do an analysis of the unsatisfiable core to see which signals we should really throw a definition in of, usual stuff, but not too sophisticated. I mean, any other techniques you could imagine applying. This is all orthogonal here.
Did you try to measure if the invariants are useful or not? How, I mean, usually it's a bunch of invariants, I guess.
Yeah.
Do you have an idea?
No, we haven't done any of these studies yet. What I can tell you, however, is that, for instance, we played with, why do we have these settings where, for instance, I don't know if I have them here, you can eliminate the trivial invariants and the redundant edges, right? Here, we are using the strong version of our invariant generation algorithm that tries to minimize the number of redundant edges, but we don't care about eliminating trivial invariants. If you set this to false, yeah, you get a tighter set of invariants, but in fact, it's not better because you spend a lot of time in trying to eliminate the trivial invariants, and perhaps since you're eliminating lemmas, you're also asking the solver to do more work. These are difficult questions to answer. We haven't done a serious study on this. But of course, it's something that should be done because at some point, you're going to swamp the system with invariants. The good thing is we've been using yikes, and I guess C3 is the same. You can throw a lot of crap at them, and they'll just go on. Right? So generate lots of invariants. A lot of them are useless. Well, they turn out not to be harmful. So we haven't been motivated so far. At the same time, our systems have been relatively small. I would imagine that our systems are big, and you have to start being careful about these things.